Hello everyone, welcome to Stochastic Calculus for Finance 1. And this is section 6.2, where we're talking about the binomial model for interest rates. And we now in part 2. So let's talk our goals for this session. First, we will give a concrete example of the binomial model of interest rates. So this is going to look like a tree, and we'll introduce that. Then on this tree, we'll show also what are called transition probabilities. Then we'll go through definition 6.2.2, which is about conditional expectations computation on a tree, for example. And then we'll use this to talk about a more general definition of zero coupon bonds. And then we will look into theorem 6.2.6, which is actually very important, which is telling us that discount reward process of a trader that is trading in the bonds and in the money market within our model. His discount reward process would be actually a martingale. So that is just another way of saying there will be no arbitrage within this framework. Okay, binomial model for interest rate. So let's assume that we have a coin and we take that coin and we toss it n equal 3 times, right? So our coin, we just toss the coin 3 times. So maybe we first the coin toss, we get a head. The second one, we get a tail. And the third one, let's say we get another head. We're listing here all possible potential outcome from this experiment. So, and then in the book, we're giving some example of some probabilities. So let's say the probabilities of getting head 3 times is 2 to the power, is 2 divided by 9. And this is in the risk neutral world, right? That's what this PT means. So these are risk neutral probabilities. But we can just think of them as just any probabilities from this experiment. So we list these probabilities out here. So just to keep in mind where I'm listing these probabilities here so we can remember. So let's say, for example, we go to the bank today. We know the interest rate is R0. The bank can tell us, okay, if you want to invest money with us for one period, let's say 1 year, the interest rate will be 3%. So today, R0 is known. But then after 1 year, if you invest at R0 1 year from now, if you go to the bank, probably the interest rate could potentially change, right? And we're saying, for example, that would be dependent on our coin toss. So we take our coin and we toss it. Let's say, for example, if it's a head, interest rate goes up to R1, H. This is the interest rates from 1 year from now for an investment that's going to do for an investment from year 1 to year 2, for example. And now, if we get a tail, maybe interest rate then is going to be reduced over the next period. And you see, we're tossing the coin, let's say 3 times, right? So maybe if the first time we get head, we come here. If we got another head, then we're coming up here. If we get a tail, we can come down here because we have like HT. And essentially, this is what this tree is showing you, right? How interest rate could potentially move depending on the result of the coin toss. And we know the probabilities of getting, for example, H 3 times in a row, right? And that probability is the probability of going through this path here. There is the probability of going through this path of interest rates. And we know this probability is 2 divided by 9. So what we can do now is we can just basically put these probabilities at the end here. So we can keep them in mind and keep looking at them. And now we're interested in finding essentially transition probabilities. What the transition probabilities are, so say for example, you're at this point here. What is the probability of going from this point to this state, right? That is the transition probability for that. And that is essentially just the probability of getting a head with the first coin toss. And to find the probability of getting ahead, that is, we take like all the outcomes where the first coin toss was ahead, then we simply sum all those probabilities, right? So in this case, that would be basically 2 divided by 9 plus 1 divided by 9 plus 1 divided by 12 plus 1 divided by 12. And essentially, when you do all that math, you find basically that is 1 over 2. And then let's say you want to find the transition probability of going from R0, from this state to this state here. Then naturally it's going to be just the same thing. That's just the probability of getting tail for the first coin toss. And you can essentially just sum up these probabilities here. And you find also that it's just simply 1/2. And then now let's say you want to find the probability, like assuming that we're like at this point, assuming that the first coin toss was a head, what is the probability of getting another head? All right. So just how this is formulated, you can think about it that this is just being like a conditional probabilities, right? So if you know probability of A given B, simple rules of probabilities, we know that there's probability of getting A and B divided by probability of B. This is very simple probabilities rules. So that's basically then, this is actually the probability of the transition probability. Given that we are at H, right? Given that we are at H, given that we are at this state, what is the probability of getting another H? That's just the probability of getting H and H for the second two coin tosses divided by the probability of getting H. And probability of getting H, we're just going to now see all the outcomes, all the coin tosses where the first two are H. Then we're going to just very simply sum that up and then divide it by the probability that the first point toss was H. And when you do this math, you'll find that is actually 2/3. And maybe we can just go through this one calculation. I'm not going to go through all these calculations, but maybe just a few of them. So probability of H, that is 2 divided by 9. Plus probability of HHT, that is 1 divided by 9. So that is essentially 3 divided by 9, which is 1/3, right? So we know the numerator here is 1/3. And we're dividing it by probability of getting H at the first coin toss. So that is basically 1/2. So you get this 1/3 divided by 1/2, and that's simply 2/3. And that is why the transition probability here is just 2/3. So nothing too mysterious there. And then naturally we can do the same thing. The probability of getting a head, probability of getting a tail, given that the first coin toss was a H, right? So that is essentially the probability. If you assume that we're here, what is the probability of transitioning from this state to this state? And when we do the math, just as usual, again, we find that's basically 1/3. And we can keep doing this for all the transition probabilities as well. So this guy here, so assuming that we will get the head, what is the probability that we're getting from this state to this state? So that is basically, what is the probability again here of transitioning from this state to this state, basically? And we can just do the math again. So PHH, probability of getting all H, that is 2 divided by 9, divided by the probability of that the first two coin tosses were HH, right? So HH, that is this is the case where we have HH. This is the case where we have HH, and that's all. So that is basically 2/9 divided by 2/9 plus 1/9. So that is 2/9 divided by 3/9, and that is simply 2/3, right? And that is where this 2/3 probability here is coming from. So very simple stuff. And we can do this also for all these different rows. And these are called transition probabilities. So if you want to find the probabilities of getting from R0 to this RHH, that's basically the probability of following this transition. From R0, we come to R1, that is 1/2. Then from R1, we move to R2, and here, that's 2/3. And from here, we move to here. Essentially, if you take these probabilities, 1/2 multiplied by 2/3 multiplied by 2/3 again, then we'll get overall this 2/9. Okay, so that's what I would say on this one. Now, let's talk very quickly about this definition 6.2. 6.2.2. So let P tilde be the probability measure on the space omega of all possible n coin tosses. So we take the coin and we toss it n number of times, right? And we define here the minimal enter-thread process. We have seen this before. And we know that Rn depends only on the first n coin tosses. Also, R0 is not random, because if you go to the bank today, the bank can tell us what the interest rate level is. So there is this thing that we call a conditional expectation. So this is the probability of getting a so maybe that we did the first coin toss, we did the second coin toss, and we did this small n number of coin tosses, right? So then what is the probability of knowing that we got this for this first n coin tosses? We know what the values were. What is the probability that next when we go from n plus that the coin n plus one toss to the last coin toss will be exactly this value here? And this is just the simple conditional probabilities that we have seen before, all right? So this is then that's just probability of A and B divided by probability of B, right? And that's what this definition is telling us here exactly. So if X is a random variable, then the conditional expectation of X with respect to information that's available at time n is just given by this expression. So, and what is saying here, let me just give a quick example here to see if we can understand it a little bit better. Let's say that, for example, we are at this point here, right? So we know that the first coin toss was a H, right? We know the second coin toss was a tail. So once we're at this stage here, what is the expected value of the interest rates, right? Well, it's simple. So we're here, then we just need to take we know the probability of going from this stage. We know this probability here. We know this probability here. And all we need to do is just basically multiply this R3HHT by its probability plus this RHTH by its probability, and then we will get the expectation as of we stand on this point here. So if you're not here, what is important is these transition probabilities, right? And that's all. And that's essentially the same thing here. So notice here, basically, we toss the coin. So from from the first coin toss to the end coin toss, this is known, right? So that means that everything that's before does not matter. All we care about is basically the transition probabilities from point n to point capital N, the end of our coin toss, right? That's why we're using these conditional probabilities, and then we multiply by the value at this end of terminal value nodes. So I think this definition is not too complicated if you just picture it, right? Then, well, we can talk about now just a revision of the price of a zero coupon bond at the future time. So the price of a zero coupon bond as of time n, for a zero coupon bond that's going to mature at time m, and let's say that the zero coupon is paying $1, then there's just given by this expression here. And to give an idea about this, so let's say here on our time frame we have m. So this is a zero coupon bond, and we know it's going to pay $1 at the end here. And we want to find it's the value of the zero coupon bond as of potentially as of this time n here. So what we can do essentially, one thing we can think about this ratio, we can think about this taking this zero coupon bond and then discount it back to time zero, right? So that means that you will multiply by dm, and then once you know the value of the zero coupon bond, then you future value it to bring it now to time n, and the way you're going to future value is by multiplying by 1 over dn, right? And then since now this is stochastic, then that means you need the expected value of all of this to find the price of the zero coupon bond at this time here. So that is essentially what this is telling us. And also, if we note that by taking out what is known, we can actually have this expression here, right? And what do we mean by taking out what is known? At time n, we know what dn is, right? Because dn, as you remember, if you remember, what dn depends only on the first n minus 1 coin tosses. So at time n, we know exactly what this dn is. So that means we can take it simply out as a constant. And then we have, that's where we're getting this expression. So now let's imagine we have a k. The k is occurring a little bit even like before n and before this m that we have here. So the expected value as of time k, right, is nothing but the expected value. So this d and bm, we have shown that this b and bn is simply this, right? So we can just replace it here. So we have this. And then notice that we have now, we can use the property of iterated expectation, right? So if you use the iterated expectation, and we know k is happening before n, then that is simply just the expectation as of time k of this value dm here. And again, we can use this property, right? So we have here, for example, if you have dm as of time n, we can just replace by dn bnm, right? So if this n was a k, then naturally we just replace by k here, and we have dk bkm. That's exactly what we have here. So what we have shown here is actually that the discounted bond price dnbm is a martingale on the p tilde, right? Because the expected value as of k of this value here is nothing but its current value as of time k, right? So we have shown that it is a martingale, and we can note it here. This is the main relationship that we have shown here, which is important and will be used again as well. So now let's talk about this thing, very important also, which is the discounted wealth process in the binomial model. So let's say we imagine that we have an agent, right, who can trade in the zero coupon bond of every maturity and in the money market, right? So let's say we have Mr. Trader here. He's ready to make quite a lot of money. And he can decide that he can trade in B01, which is basically the price today of a zero coupon bond that pays $1 at time 1. He can also decide to buy B02, which is a bond a zero coupon bond that matures at time 2, right? And then B3 up to a set of n to the n number of zero coupon bond that he can trade in. And he can short them, he can be long some of these bonds, anything he wants. So now let's call basically, we're going to call delta nm the number of m maturity zero coupon bond that the agent will held at time t, which is between n and n plus 1. So this is just basically the number of shares that the trader can decide to trade in. So maybe at time 0, he can decide that he will hold delta 01 shares, delta 01 unit of this zero coupon bond that pays $1 at time 1. He can also decide to hold delta 02 number of bonds and which bonds, the bond that's going to be maturing at time 2, etc., right? So we can think about this as the number of units that he's holding for each of these bonds. And we can define xn, the initial wealth of the trader. So this guy, he has in his bank account at the beginning, he has this amount of cash, and from this amount of cash, that's what he's going to use essentially to trade and try to make money, make a living for himself. And then naturally, if you want to think about what his wealth, then his wealth kind of evolve following this equation here. And this equation actually might look a little bit strange, but it's actually very easy to understand. So the trader at the beginning has this much pile of cash, right? And from this pile of cash, he can decide to buy. To buy some of these bonds. So maybe if he buys like a 3 share of B1, so that means that he's taking this cash, and then he's minusing delta 1 share time B01, right? And then maybe he's going to buy also delta 2 shares of B02, maybe he's buying delta n share of B0n, right? So that means that when he is finished doing that, the cash is going to be left is going to be basically he has his initial pile of cash minus how much he spent to buy these bonds, right? And that is exactly what is presented here. This is the initial amount of cash he has minus how much he spent to buy all these bonds. So he's buying delta shares of this bond, and then he has many different bonds he can be buying. Maybe a bond maturing at time 1, a bond maturing at time 2. So that's that, right? So when he's left with this cash, the cash he's left with, since we like at time Rn, is going to be invested at the interest rate prevailing in the market at that time, right? So that means that at time xn, so that means that at time n plus 1, the remaining cash he has will grow to 1 plus Rn. So that's all that is for that first part. So I think now we understand where this part is coming from. Now, what is this guy here? So at the beginning, let's say like he bought among his portfolio, he bought a delta 02 shares of B01, right? So at time 1, one step from now, so at time 0, he bought some stuff. At time 1, what is the value of this? Well, that's the number of shares that he bought at the beginning, right? Multiplied. Now this bond, his bond here, is have a new value. It's had the value of the bond at time 1 of the share of the bond that's going to that matured at time 2, right? And that's exactly what you're seeing here. We have here the number of shares that he initially had, but then now, since we're like at time n plus 1, this we have n plus 1 here for this for his bond, and that's pretty much all that is. So naturally, his wealth is going to evolve. Then I think you're seeing it here. His wealth is going to evolve following this this equation. So something interesting, like regardless of how he's trading, regardless of how many shares that he decides to hold this bond, and you can think about the set of deltas, all right? This set of deltas are his strategy. So maybe his strategy is okay. He's going to long three shares of B01, and he's going to short 5 shares of delta 02, right? So depending on how he's choosing this delta M, that is what's going to define his strategy. And what we're saying is no matter what strategy he uses, his discounted wealth process, delta nxn, right? So this is his discounted wealth process. When you take his wealth in, no matter what that strategy is, you discount it to the present, that is going to be a martingale on the natural measure. And by being a martingale, what we're saying is essentially there is no arbitrage opportunities. If his initial wealth is 0, then there is no strategy he can employ by trading in these 0 coupon bonds and the money market, such that he will have at any future time an expected value that when you discount is going to be positive. And that is all that we're saying here. So now let's show that this is actually true, that no matter what strategy he uses, he cannot make extra cash. So what we want to show is this relation here. And we know the discounted wealth process is evolving following this equation. So we're going to just make a note of here to not forget about it. So now what we're doing here is we can simply take the expectation on both sides, and that's what we're seeing here. Then now if you pay attention, you will see that what we did here, this n plus 2 before was n plus 1, right? But then so when we take this n plus 1 out, so delta n m becomes delta n plus 1, right? And the value of the 0 coupon bond as of time n plus 1 that matures at time n plus 1, and the 0 coupon mature, that's going to give you principal of 1. That is all here, right? And then what we're doing here is we're just taking this expectation and bring it inside. And here, well, we're taking the expectation as of time n, right? So at time n, we know exactly what Rn is. Rn is really dependent only on the first n coin tosses, right? So once you toss the coin n time, we know exactly what Rn is. So this is not random. Xn, the value for what at time n is also known. If you are like because we toss already the coin n times. And bn at time n, we know exactly what the value of the zero coupon bond that's going to match the future time m is as well. So that's all we have here. Then what we can do is we can basically take this, divide by dn plus 1 like we're doing here, and then multiply by dn plus 1. And if dn plus 1 can be inside, because if you remember the definition that we have also of dn, if you notice, depends only on the first n minus 1 coin tosses, right? So that means that at time n, dn plus 1 depends on the first n coin tosses. So that means it can be taken out, it is null, and we can multiply also by the same here. And finally, if you look here, what we did here is we replaced this value 1 plus rn by this ratio. And again, this is not very surprising because imagine you have dn at the numerator, right? So you're just multiplying, you have this 1 divided by 1 r0 up to rn plus 1. And when you divide, on top you have the exactly same values, but you will have probably just an extra rn, right? And they're going to cancel out. When they all cancel out, you're just going to be left with this 1 plus rn. And you can verify this. I don't think it's too deep. Okay, then now we can start making use of some properties, right? So we said the discounted bond price is a martingale. So that means what we can do is we can replace this expression here simply by that, right? Because we know that it's a martingale. And this dn plus 1, so what we did, simply what we did here, all we did here essentially was expanding this iteration. So when you take this guy, you multiply by xn, that's what's coming here. And then dn plus 1 multiplied by minus this summation here. And that's all. And when we do that now, this guy stays the same. So we're taking this expression here and then moving it across. We're taking this, so we take this dn and this n plus 1, move it outside of the summation. And then we just get this expression here. So nothing too surprising so far. So from here to here, yeah. So once we move this expression, so here let's say here you notice here we have n plus 2, you have here n plus 1, but this expression is exactly the same, right? So that means when we do the subtraction, we're going to be left just with n plus 1. All right, so that's where this is coming from. So this expression here is just coming from this from subtracting these two together. And then here we just bring it back down here. We're just copying, nothing new there. So now let's look at this expression, right? So we have this guy, we don't touch, but then let's look closely at this bn plus 1. So this bn is plus 1 is essentially, let's say we're standing at time n, right? And we have a zero coupon bond that's paid $1 and we want to find the price. So all we need to do is discount. But at time n, we know what this interest rate that we're going to be discounting by is. It's just Rn. We know that, right? So that means bn plus 1 is simply equal to this. And this Rn, as we have, just the same thing as we have shown here outside, we can replace by this ratio, essentially, very simply. And when we do that, then if you look closely now at this expression here, so that means this dn is going to be canceling out with this dn here. This dn plus 1 is going to cancel out with this dn plus of here. So that means these two are canceling each other. So we have delta n plus 1 minus delta n plus 1. So these two are going to cancel with each other. And then we're left with simply with this, right? And so we have shown that the expected value as of time n is equal to this. This dn plus 1 can be just moved inside this expectation here. And essentially, we have proved what we wanted to prove. The discount wealth process is a martingale on the P tilde. There is no arbitrage for the trader. Okay, so Nick and now recap very quickly. We introduced the binomial model for interest rates, talk about the transition probabilities, conditional expectation, revised the definition of zero coupon bond based on conditional expectations. We proved that the discount wealth process is a binomial. So now we have really a model that doesn't allow arbitrage. So then going forward, we can use this to price things like caps, floor, or other interest rate derivatives. All right. Thank you very much all for watching this video. I hope you find it helpful. Thank you.